Okay, so good morning, everybody. So as Elwin said, it's very time limiting. So it's my pleasure to be the first session chair, and the first speaker of the morning session is David Parkinson from CASI. Hi, David. Are you ready?
Hi, yes, I'm ready to go.
Okay, so can you share your slides? Okay, very good, very good. It's all visible. So, okay, so David will be talking about large scale distribution and radial continuum galaxies. So please go ahead.
Okay, so I'd like to thank the organizers for inviting me to speak. So this is some work that I've been doing on the large scale distribution of radio galaxies. And this work is in collaboration with Hakabo Osori, Benedict Callas, Stefano Camara, Catherine Hale, and Faye, and the members of the EMU and RAX collaborations. So, did everybody see my slide move occasionally on Slack? Occasionally on Zoom, like slides don't move. It moved for me, it's all good. Okay, I'm just going to assume it's fine. So I'm going to go very briefly again on what isotropy and homogeneity are and how you might test them. And then I'm going to talk about some large area radio surveys, in particular outlining what the future looks like in this sector. And then I'll speak specifically on RAX and EMU before I summarize. So if we're going to make statements about cosmology, it might be good to distinguish between what the observable universe is, that is, the universe that we can observe, and then the universe. I've taken this Flammarion engraving because it's a great picture, but I give a roughly even odds that this won't be the last time that this image appears in the slides this week. So the universe is a different sort of thing that we talk about, and it includes regions that we can't directly observe or influence or experiment on. It's regions outside of our light cone. And so when we talk about the sort of the cosmological principle, we are in fact making statements which aren't simply about what we observe, but also about the universe as a whole. So what we mean by isotropy is the observable universe is the same in every direction. So the sky at night seems roughly isotropic, unless you're in the south when you can see the galaxy and the imaginary clouds. But beyond our Milky Way galaxy, the galaxies and the cosmic microwave background seem to be roughly uniformly distributed on the sky, at least as far as we can observe. And there's some discussion about this, of course. But to some level, there is no massive structure that we can immediately obviously see. So the observable sky at least seems to be rotationally symmetric about any particular axis. But homogeneity is a different thing. Homogeneity means that the universe is the same everywhere. Not that it appears to be the same everywhere, but that it is the same everywhere. Of course, we know our understanding of cosmology knows that the universe is not the same over all time. It starts at a high density in the distant past and then expands. And so the homogeneous density, the average density on constant hypersurfaces is not the same. It will slowly evolve. And obviously the universe is not homogeneous on very small scales, right? There are planets and stars and galaxies, etc., with vacuum in between. It isn't like one contiguous fluid. So when we talk about homogeneity in the sort of cosmological context, it means that on some large scales, some rough scales, maybe around 200 megaparsecs or more, it can be assumed to be smooth-ish, smooth enough that we can do things like compute luminosity distances or compute angular diameter distances, etc. So how do we go from one to the other? Well, we start with the principle of mediocrity. This is Nikolai Copernicus, who basically said, actually, you know what, maybe we're just average. Maybe we're not at the center of the universe after all. And so if you start from the principle of mediocrity, that we're just some random instantiation of existence, but the universe looks to be the same from our position, from our observational position, then if we combine these two, then it probably looks to be the same to any other observer. Universality plus the Copernican principle plus isotropy leads to an inference of homogeneity. If it looks the same everywhere else to everyone else, then it probably is the same everywhere else. But homogeneity is much harder to test in this case than isotropy. With isotropy, we observe the sky, we're just making statements about what we can see from our position. But from homogeneity, we're making statements about what everybody else can see as well. So the cosmological principle then holds that the universe is isotropic and homogeneous everywhere, even beyond the bounds of the observable universe. Okay, so how do we test this? It's not to say that people haven't tried to test this, of course. There's this sort of classic homogeneity test where you take a galaxy survey, a galaxy sample, and you sort of count the number inside some radius, some spherical radius, and you slowly expand that sphere, and you look at how the number count differential changes, and you can measure the sort of fractal dimension of the structure that you're measuring at that point. So, for example, and this is some work that was done by the Wiggles team. I was a member of the Wiggles team back when that was still a going concern, where we took this large sample, and you can do this. If you cover enough volume, you can see when the sphere becomes large enough, you have this convergence to homogeneity. If you only do it on small scales, you might get this filament, right? This is a galaxy simulation with a filament where it doesn't go as 1 over r cubed, it goes as 1 over r. Right? You're just counting the number of galaxies along the filament. But as you get something which is large enough and these local structure concerns disappear, then you should get, your standard number of dimensions. But of course, in order to convert a galaxy sample into something which is a 3-dimensional distribution, you need to convert from redshift to distance. And in order to do that, you have to assume some distance redshift relation, and we do that using freedom. Right? We go we start with angles and redshifts, and we convert that into some Cartesian distribution, some 3-dimensional distribution, assuming that distance redshift relation holds. So, and we're kind of testing, in this case, we're kind of testing homogeneity, but I'm assuming homogeneity, right? Which is good as a consistency check, but it doesn't necessarily make it a model independent test. And the alternative then, of course, which doesn't require you to make that transformation, would just be an isotropy test, right? Which checks the angular distribution of galaxies on the sky. So I'm going to talk a bit, basically more about this for the remainder of my time. And I'm sure that other people such as Dominic, etc., will return to this later. And the main concern here is that although it is cosmology independent as a test, it is you're still dominated by local motion or local structure. So this is a simulation of what it would look like for something like the SKA, the square kilometer array, taken from the SKA Red Book, where the big blue dot is the direction of the CMB dipole, and then the dots are the recovered from a simulation which direction the dipole would be. And so the sort of local structure dipole could be anywhere on the sky, right? Depending on your initial conditions for your simulation. But if you take that structure into account and then try and remeasure the kinematic dipole without reference to local structure, then you get a nice grouping of red dots around the true answer, which is the CMB dipole. Okay, so the remainder of my talk will really be talking about how we can try and test these ideas using radio surveys. So what do I mean by an radio survey? So at the moment, most major cosmological results, if we consider cosmological inference, have come from the CMB. The CMB is the most powerful existing cosmology experiment at the moment. And it has reached the limit, though. The Planck is now cosmic variance limited, at least in the temperature power spectrum at larger scales. And although optical galaxy surveys are coming up and they're powerful in their own way, they are limited in some ways in comparison to what you can do with the CMB. Partly because they're a discrete tracer of the density field, and they also exist at low redshift, where the physics is nonlinear. So at the moment, or until very recently, the radio where you, again, could be measuring a discrete or a continuous density field, and low up to what I call medium redshift, which is sort of things much higher redshift than we can do in the optical. But that's really lacked the number density, the total number density, to be a serious contender. Until just a couple of years ago, there were only roughly 2 million extragalactic radio sources that have been detected in comparison to the tens or hundreds of millions of extragalactic optical sources, optical and near infrared. But radio has some advantages. It doesn't have a problem with dust obscuration, and observations can be made much faster, as I will show, if you have the right pieces of equipment. And so this might allow us access to this very large scale of information, things like the dipole or primordial non-Gaussianity, sooner than waiting for optical surveys to come. So how do we get cosmology from radio surveys? We can just look at, there aren't many lines in radio galaxies. There is the 21 centimeter, so you can just do the equivalent of an optical galaxy redshift survey, but in the radio using neutral hydrogen. You can also measure peculiar velocity through the Tully-Fisher relationship in principle. But this sample is kind of limited, both in redshift and both in number counts. And so it may be better to look at other things you can do in the radio, things like the continuum survey, continuum where you're just looking at the synchrotron emission, so you have this very flat spectra, and you don't have redshifts in that case, but there's still a lot you can do with an angular clustering survey. Or to flip it, rather than being delocalized in the radial direction, you can delocalize yourself slightly in the position on the sky with a 21 centimeter intensity mapping survey, where you're measuring redshift and position, but in a slightly more fuzzy way. And you can still use this like a spectroscopic survey, and you get something which becomes competitive with the nuclear satellite, but you can do from the ground. And then, of course, you can do like a weak lensing shear, where you're looking at the shape of these radio sources and how they are lensed by the intervening structure. So I'm really going to talk about this one, the Continuum Galaxy Survey. And so I'm going to talk about this very briefly and skip on, but there are existing radio telescopes right now which are still more powerful than any radio telescope ever built before. And these are just the precursors to the square kilometer array. So there's the Australian Square Kilometer Array Pathfinder, which is the survey instrument. It's really the precursor to some kind of survey facility for SKA. There's the Murchison Wide Field Array, MWA, which is the precursor to SKA Low, really targeting that epoch of reionization science. And then those two are in Australia. And then in South Africa, there's Meerkat, the Karoo Array Telescope, which is the precursor to SKA Mid, which again is sort of built, it can do some survey stuff, but it's really built to do sort of pulsar science and this high resolution science. And then there are also other experiments going on, being built in parallel. These 21 centimeter experiments, such as CHIME and Tianlai, CHIME in Canada and Tianlai in China. These are these sort of long cylindrical arrays that can scan, which don't have good angular resolution, but are built for 21 centimeter intensity mapping. There's also HIRAX, and which is a similar thing. And then in Northern Hemisphere, in Europe, there's LOFAR, which are these dipoles, again, kind of similar in wavelength range to MWA, yeah. Okay, so how can you do cosmology? If we're just interested in continuum sources, how can you do cosmology with these? So you can just look at the angular distribution, which tells you something about the structure. You can measure the cosmic magnification, whereby you do cross correlations. You take your radio sources at high redshift and you cross correlate them with your optical sources at low redshift, and you see the effect, the brightening or dimming of the distant sources by the intervening structure. And then you can flip that. Instead of the radio galaxies becoming your sources, they become your lenses, and the CMB becomes your sources. And again, look at a cross correlation between your radio density and your CMB distribution on small scales. But on large scales, there's also a different effect that happens, whereby you have a redshift or blue shift. You have an energy boost or decrement caused by the CMB photons coming through the intervening structure, which is the integrated Sachs-Wolf effect. And again, you measure this by cross correlations. So you're taking these angular distributions, you're still doing everything in a sort of redshift, you're still taking your data products in a redshift independent fashion, but by making cross correlations between these angular distributions, you can try and probe these different physical effects. So this is, when I talk about correlations, I mean spherical decompositions. So these power spectra on the surface of a sphere using this standard basis set, right? The spherical Bessel function basis set. So we describe the distribution of galaxies or the CMB, to be honest, through some displacement field. We decompose it, and then we have these CL power spectrum. This is when we talk about the CMB, we have this CL. This is the definition, but it's exactly the same for galaxy distributions. We can do exactly the same physics. So that this CL really doesn't make an assumption about the way that you've taken the data. It's just taken some distribution and decompose it. The trick then trying to compare that to your prediction. Oh, and there's the angular correlation function, but it's just the Jiro transform in this case. It's just another way of representing the distribution of power on the sky. So how do we connect measured correlations to cosmological parameters such as density of matter, etc.? We have this long equation which infers what the CL should be in terms of the underlying matter power spectrum, but also the distribution of your underlying populations. So for the CMB, that's easy. It's just photons coming to you from recombination. But for the galaxies where you have this distribution in the sky in the radial direction, that window function can be much more difficult to understand and can become confused with your cosmological signal. So if you want to do cosmology with this kind of sample, you need this large sample. This is our shopping list on the right-hand side, a large sample over a large area with very few holes or gaps that can easily, hopefully, also be subdivided. And that isn't necessary, that just adds to your utility. And then for your theory understanding, you need your known population with a known evolution and a known bias and a known luminosity distribution. And some of this understanding of the population may become confused or confusing with your prediction for what the cosmology is telling you is going on. Okay, so I've gone through all the sort of theory. I'm now going to talk about data. I've got a few minutes left. So I'm part of 2 radio continuum surveys. There's EMU. EMU is an upcoming survey. We've already taken some pilots, studied survey data. It will cover the entire southern sky with ASKAP. So that's up to declination plus 30, in fact, so quite a bit of the north as well. So about 30,000 square degrees, 3/4 of the sky, to a depth of about 15 microdowskis. So that's really, well, a noise level of 15 microdowskis. So that's really pushing far with these huge numbers of galaxies. It's an open survey. In fact, if you have some science that you want to do, you can just apply to join. We're not just doing cosmology. There's galaxy evolution, star formation history, evolution of AGN. All this kind of science is being done by EMU. So yeah, so if you want to join, you can contact one of the EMU management team. So these were the pilot observations that were done back in 2019 now. It feels so long ago. This is 10 regions with 10 hours integration per region. And this is what the data looks like. But of course, there are these patches. I don't know if you can see my mouse, but on the right-hand side, down in the bottom right, you see this sort of hole. And you see a patchiness around the edge. And this is just due to the way that the data is taken. So you can fold in your noise map. So here we have our number counts in pixels. This is just the number of galaxies in each pixel. Here we have our noise map showing where the noisiest regions were, which allows us to make random catalogs. And when we combine, and then when we use these random catalogs, we see the same kind of structure. So this hole in the bottom right-hand corner matches what we see in our data. So our randoms in our data look pretty consistent. And then we can measure our angular correlation function. And we can make a prediction. And I didn't do any fitting here. So we have our data in our angular correlation function. I make some Planck prediction And I don't need to change any of the parameters, right? I didn't fit for omega matter. I didn't even fit for the bias very well. I made an estimate based on simulations, which are the scan simulations. And we have something which is already remarkably consistent with what we would expect from Planck. It's not measuring it very well at present. In fact, if we try and then measure omega matter, we have quite a large range of allowed values, and it's very degenerate with the bias as well. But this is just from a small region of the sky. This needs to be redone. So I'm in the process of reanalyzing this right now. Even with this 10 field data we get something that looks roughly consistent. Okay, but what about all sky, right? If we're going to measure isotropy, if we're really going to test the dipole, we need an all sky survey. So here comes RACS. So RACS is the Rapid ASKAP Continuum Survey. So again, RACS is kind of a precursor of EMU, where instead of doing 10-hour integrations, we just did 15-minute integrations, right? Really trying to push this thing to see what we could do in the shortest amount of time. And again, covering roughly 2/3 of the sky, 60%, everything up to +40 and 903 tiles. And will the video work? Yes, so this was how it worked. So we have the sun in yellow, the moon in purple, and then the blue regions are the regions which are being observed. And then this is just a few weeks' work, basically filling in the entire sky with these 15-minute integrations until it's all done. So I don't know if you saw, this was the date at the top. So it finished on the 8th of May, and it just started on the 21st of April. So really, when I talk about like being able to survey the entire sky very quickly, I mean, 15-minute observations are too short, right? We only ended up with about 1.26 million galaxies, which is not much in comparison to what we should be possible. But this is my sort of demonstration about how quickly radio observations can be taken. So this is our source density with RACS. Here we just pixelized and normalized, and this is just, again, each pixel represents some distribution of galaxies where a blue color is not very many and a yellow color is a lot. And you can see that there's a lot of blue around the edges where you have beam dropouts. So you wouldn't expect to be complete exactly around the edges. And we also have these patches where, for whatever reason, radio frequency interference or some other technical reason, we don't exactly get back what we would expect. But again, we can use the noise map. This is our noise map. It shows where we were noisy. And we can combine our density field and our noise map to get roughly what we feel is the true distribution of galaxies on the sky. This is our number density weighted by the noise or our observation efficiency. So we can measure our large-scale angular power spectrum for this, and we get something like this. We get this, in fact, so here we've made some simulations using the full sky log normal astrofield simulation kit, or FLASK, with some CAM input power spectrum, and we see some, and then the data are our crosses, and we've done a large number of simulations here, and so we can count what we'd expect from our simulations. So in darkest we have 1 sigma, and slightly theta 2, and thetis 3, and as you can see, we have a large scale power excess. On small scales we get what we'd expect, but on very large scales we have a power excess, which is slightly disappointing, given that we're unsure where this is coming from, right? Is this a systematic effect in the way that we're taking our data, or is there a real large-scale power excess on the sky in terms of the radio galaxies? And we broke this down by declination as well. So what we did was we just took strips in declination and we measured the power spectrum in these strips. It's a lot noisier because you don't have the full sky, but we get something where the power seems to be roughly consistent with the prediction close to the pole, like -70 to -80. We have this large scale point down here. But then as we go towards the equator, we see that power excess really start to rise. And in fact, similar behavior has been observed with NVSS. This is a different data set to NVSS for a start, because it's at a slightly different frequency, 978 megahertz compared to 1.4 gigahertz in NVSS. and it's in the south as well, whereas MVSS was observed in the northern sky. So again, it's difficult to know what's going on here. Are these? It's not a Doppler. It's not a Doppler effect. It's not like a Kaiser rocket or something. There is some systematic or cosmological effect. Unsure at the moment. But since we have the data set, we might as well also try and measure the integrated Sachs-Wolf effect. So again, we make all these simulations. We cross-correlate this time with the CMB. So here our null model is one with no cross-correlation. And again, we find something different to no cross-correlation. This time we would expect that though, because we think the dark energy exists. The dark energy would introduce some non-zero cross-correlation, and indeed we see that. We have a detection of about 2.5 sigma of the ISW effect. Okay, so I'm going to finish up there. So radio continuum surveys can be used to trace the distribution of matter in the universe. They can be used to determine the initial conditions, detect the effects of the dark energy, and test the isotropy homogeneity of the universe. So EMU and RACS are radio continuum surveys that are being made using the Australian Square Kilometre Array Pathfinder, or ASKAP. I've got the number there, but it's 1.26 million galaxies detected by RACS we use to detect the effects of the dark energy through the ISW effect. But we also see a large-scale power excess, which is different to what we would predict from cosmology. And is this a systematic error or some physical effect? And then with EMU in the future, just a few years' time, we will have roughly 40 million galaxies and provide a much more significant measurement of this effect. And thank you very much for taking the time to listen.
Okay, thank you very much. So if you have some couple of quick questions, you know that after the morning sessions, we have ample time for discussions where you can ask anything you like regarding the opportunity that radio cosmology will provide us. So you may leave extensive questions for the discussion session, and you may, I think, ask a couple of quick questions. So, oh yes, Dragon, please.
Hi, hey, David, this is Dragan Huterer. Very, very nice talk, very interesting stuff. Just a very quick comment in the spirit of Jiro just told us those power spectra you're showing with excess power at low L's at large scales. This is, as you probably know, this is exactly the kind of thing you see in, I think literally every large scale structure survey has seen this or would have seen this without further cleaning of various calibration errors, many of which look like excess large scale power. So this is a classic thing that happens for all kinds of reasons in large scale structure. And so it requires further dealing with to remove. So it's not very surprising at all, I think.
No, we were hoping to be able to deal with it, but yeah, we've done our best in terms of the way that the randoms are generated, but it's still sticking there. It's probably some very subtle points. Yeah.
And there's one question from Joby. David, can you see it? You can see the down Q&A.
Yeah, given the finite number of radio sources, at what resolution do you expect the source field to be approximately a continuous distribution? I mean, I kind of hope, it's going to sound weird, but I kind of hope that it's never a continuous distribution, right? Because at that point, then you reach the sort of confusion limit where the radio sources are overlapping and you don't have a single radio source anymore. You just have this mess of things. And that's a slightly complex question to do with the way that the radio observations are made. Depends on your angle. It doesn't just, so you could be confusion limited now with EMU if you weren't operating at 10 arcsecond resolution, right? So with EMU, we would already be there if we didn't have that. If we didn't have that large area distribution of arrays. So, and then with SK will have longer baselines. If we were to do this survey with SK, we would hope to be able to get down to sort of 1 millijansky RMS, maybe 5 millijansky RMS. But again, we would need those long baselines in order, not the longest, of course, but longer baselines in order to not hit that continuous distribution. because at that point, then it really becomes very difficult to measure power. At 21 centimeter surveys work slightly differently because you can pick out the redshift, but for the continuum, I kind of hope that you always have these discrete distributed structures.
Okay, so is there any other questions or comments? Okay, so if not, let's thank David again. And please, David, wait for the discussion session. There should be a lot of questions, I hope. Okay, so thank you very much. So the next speaker is Jiro Soda. So Jiro, are you there?
Yeah, can you hear me?
Very good. So it's very, very nice to see you, although it's online. So please share your screen.
Okay.
Okay, so yeah, we can all see it. So next speaker is Jiro Soda from Kobe University, and he will be talking about anisotropic inflation. So Jiro, please go ahead.
Thank you. So first of all, I would like to thank the organizer for giving me this opportunity to talk on this topic. Today, I would like to discuss the cosmological principle from the perspective of the inflation. Okay. As you know, modern cosmology is based on the belief that the universe, the present universe, is isotropic and homogeneous. That is the cosmological principle. So the cosmological principle tells us that the universe can be well described by the following metric, so-called FR-W metric. Here, you also have to remember that the present universe stems from the inflation. If the inflation universe was completely isotropic, the cosmological principle would be a natural consequence of inflation. However, it's known that anisotropic inflation is also possible. Thus, a natural question is to what extent does inflation allow the anisotropy of the present universe? So the key to answer this question is the symmetry breakdown during the inflation. As you know, the quantum fluctuation generated during inflation give rise to the CME temperature fluctuations. And inflation can be approximated by the digital universe, which has the maximum symmetry. And this symmetry can explain the Kobe data. So in a sense, CMB data have something to do with the space-time symmetry. But after WMAP and Planck, we got more precise data. In fact, inflation is not exactly digital. Symmetry breakdown is crucial for describing a realistic universe. In fact, the symmetry breaking can explain the Planck data. So the data also indicates the breakdown of rotation symmetry. And the breakdown of rotation symmetry during the inflation may give rise to the anisotropic inflation. And as a consequence, there occurs the statistical anisotropy of CMB fluctuations. The breakdown of rotation symmetry would also induce a violation of the cosmological principle. Therefore, the statistical anisotropy of CMB fluctuation is correlated with the space-time anisotropy. Since the statistical anisotropy is severely constrained by Planck data, we can also constrain the anisotropy of the present universe. This is a strategy to constrain the anisotropy of the present universe. So the plan of my talk is as follows. First, I will explain the Kobe level understanding of CMB and proceed to the Planck level understanding of CMB. And from the data, I will discuss from the data, we know that there may be a breakdown in rotation symmetry, so we consider the anisotropy inflation. And as a consequence, we discuss the statistical anisotropy. And finally, I will discuss anisotropy in the present universe. Okay, let me start with the Kobe level understanding of the CMB. here you can see the Kobe map and the galaxy distribution. All of these observations tells us that the nature of primordial fluctuations as follows. Namely, we have the statistical homogeneity and the statistical isotropy and the statistical Gaussianity. And the resultant power spectrum is scale invariant. You see here, this part is the data coming from the Kobe. So we'd like to understand this nature of primordial fluctuation starting from this symmetry. Here we consider minimal single field in chaotic inflation. There we have shift symmetry in field space, which lead to the Dojita inflation. Dojita spacetime is given by the following metric here. So this metric has the O41 isometry. We have the spatial translation symmetry. As you can see here, we have a Euclidean space, three-dimensional Euclidean space. So apparently we have a translation symmetry. And we also have rotation symmetry because this is Euclidean three-dimensional space. And here R is just a rotation matrix satisfying this relation. And on top of this symmetry, we have the temporal Dojita symmetry. If you shift time coordinate by a constant C, then you will get some factor here. But you can observe this factor by rescaling spatial coordinate, like this, okay? So this is an isometry. So we have these four symmetries. This symmetry tells us that the nature of primordial fluctuation. Suppose there is primordial fluctuation theory. First, shift symmetry implies Gaussianity. In principle, we need to consider endpoint correlation function, but because of the Gaussianity, we can only consider two-point correlation function, which is here P theta. P is function of the wave number vector K1 and K2. But spatial translation symmetry implies statistical homogeneity, which means that this two-point function is proportional to delta function. Okay, so now the P is function of K1. And moreover, rotation symmetry implies statistical isotropy, which tells us that this power spectrum is a function of only of the magnitude of this wave number vector K. And finally, temporal Dojita symmetry implies scale invariance of the power spectrum because this curvature perturbation conserved in time. Therefore, we have the spatial scale invariance that implies the scale invariance of the power spectrum. So we have succeeded in understanding Kobe results starting from the symmetry. However, now we have the more precise data. You see that this is Kobe map, and this is W map, and this is Planck map. So you can compare these maps, then you understand the data is more precise, quite precise. And these precise data tells us that we should look at the fine structure of fluctuations. So this map is almost isotropic, and this power spectrum here, we have the small tilt. If NS is equal to 1, then we have completely scale invariant power spectrum, but Planck data tells us that this is 0.968 It's apparently deviate from the scale invariant state. And there may be a chance to have the non-Gaussianity, although this is consistent with Gaussianity, but still we have the chance to have non-Gaussianity. So to understand these precise data, we need to consider breakdown of the symmetry. First, we would like to discuss breakdown time translation symmetry. So the scale of inflaton field must have time-dependent wave. Otherwise, inflation does not end. So we have this wave. So this wave breaks the time translation symmetry. So this breakdown the temporal digital symmetry lead to spectral tilt. Spectral tilt is represented by this formula. Here, epsilon and delta are the threshold parameters. And this potential also breaks the shift symmetry. Then this leads to the non-Gaussianity, which is of the order of the threshold parameter. Okay. On top of these results, W map and Planck tells us there are some CMB anomaly. For example, these people have shown that there is hemisphere asymmetry, and we can also see multiple alignments. So that tells us that there is a preferred direction in the universe, and they also insist that there is a power spectrum anisotropy described by this power spectrum, direction-dependent power spectrum. This P0 is the isotropic part of the power spectrum, and here N is the preferred direction here. So this represents a quadratic deviation from the isotropic power spectrum. The amplitude is represented by this G, and the result tells us that this is about 0.1. So there is some deviation from the isotropic power spectrum. So the breakdown the time translation symmetry can explain the Gaussianity and the scale invariant deviation from scale invariance, and the breakdown the shift symmetry can explain the deviation from the Gaussianity. Now there is a statistical homogeneity, but it is very difficult to break this statistical homogeneity, because in order to have in order to break this statistical homogeneity, we need to have the inhomogeneous inflation. So we concentrate on this part, statistical isotropy. This to break statistical isotropy is relatively easy. If you have the breakdown rotation symmetry, then you can make the you can break the statistical isotropy. For example, if you have the time-dependent wave of the gauge field, which give rise to a physical mechanism for the statistical anisotropy. Okay. So let me discuss. Let me explain the anisotropic inflation. Here we have the simple model. MP is the Planck mass, and this is Einstein-Hilbert action, and this is the kinetic term of the inflaton, and we have the potential here. As a potential, we take the exponential form. Here, lambda is a coupling constant. In this case, it's not well known that there exists isotropic power of inflation described by this metric. If lambda is sufficiently small, we have the accelerating universe, that is inflation. This is so-called power of inflation. And we have the inflaton field, exact solution of the inflaton field here. So the question is, what happened if a gauge field exists? Of course, gauge field cannot feel the expansion of the universe because of the conformal imbalance. However, if the gauge kinetic function present, then this gauge field feels time dependence through the inflaton field. So because of that, gauge field can remain during the inflation. For simplicity, we will take the exponential form for this gauge kinetic function. Here, rho is the coupling constant. And let the direction of the gauge field to be z-axis, then we can take the isotropic metric. Instead, we take the Bianchi type 1 metric. Here, alpha represents the isotropic expansion of the universe, and sigma describe the anisotropic expansion of the universe. For this parameter G region, lambda and rho are the coupling constant. We found the following new solution, exact solution. Here, omega is represented by the coupling constant, and theta is also given by this one. So omega describes the isotropic expansion of the universe. Then if lambda is sufficiently small, this describes the accelerating universe, that is the inflation, okay? So but in this case, theta is not there. So this describes an isotropic accelerating universe, and this we call the anisotropic inflation. In this case, phi takes the similar formula, and we have bevel of the gauge field. Here, gamma is represented by this one. So apparently, this expansion is anisotropic, and its degree of anisotropy is given by the following formula. So sigma over h is the anisotropy, and you can calculate the, since we have the metric, you can calculate this expansion rate, and you obtain this formula. Here I takes the value between 0 and 1, and here epsilon h is a slow roll parameter. So this anisotropy must be less than 1. Actually, this can be rewritten by the ratio between the energy density of the gauge field and the energy density of the inflaton field. So in this case, the anisotropy is oblate type, but you can make the prolate type anisotropy if you consider the non-abelian gauge field. Okay. So also we have discussed anisotropy inflation in the context of power inflation, but the result is generic, and there is a universality starting from this generic potential with generic gauge kinetic function. You can find the anisotropic inflation. This anisotropy is characterized by this ratio between energy density of the gauge field and the energy density of the inflaton field. This anisotropy leads to the statistical symmetry breaking in the CMB. Namely, we have the statistical anisotropy in the curvature perturbation. This, starting from this metric, we can calculate the power spectrum, and we got this result. Here, we have the quadratic deviation from the isotropic power spectrum. this G amplitude G theta is represented by this formula. Here epsilon is the slow parameter, and this is a space-time anisotropy. And nk is the E-Fourier number from the horizon to the end of inflation for each mode k. So now we can discuss the anisotropy in the present universe. We have shown that anisotropic inflation leads to the statistical anisotropy, but this amplitude G star here is constrained by the Planck data. Here is the result. You can see that G star, because of this standard deviation, G star must be less than 0.01. And this result, this constraint is consistent with that obtained from the WMAP data by Kim and Komatsu. Then we can say that G star is G theta is less than 0.01. So we now have the main result. As I have shown, anisotropic inflation implies a statistical anisotropy given this way, and the CMB observations give us the following constraint. And taking into account the formula for the space-time anisotropy, we obtain the constraint on the anisotropy of the early universe. Here, sigma h is just this ratio. This ratio can be rewritten using in terms of this amplitude of the statistical anisotropy. Then you get this formula. And we now have the constraint on this amplitude, which is 0.01. Then you see the space-time anisotropy should be constrained by this value. For example, for the E-Fourier number 50 and the slow parameter 0.01, we have the constraint on the space-time anisotropy sigma over h, which must be less than 1.7 times 10 to the minus 9. This is the anisotropy after the inflation, okay? Just after the inflation. After the inflation, universe evolves, then the sigma over h evolves as follows. Here A is the scale factor. Therefore, if you take this different number, then you will get the constraint on the space-time anisotropy at present. Sigma over h must be less than 10 to the minus 30. So which is quite tiny. Okay, let me summarize my talk. The cosmological symmetry may originate from inflation. Inflation could be anisotropic. Anisotropic inflation leads to the statistical anisotropy of CMB. And CMB constraint, CMB observation constrains the statistical anisotropy. The constraint on CMB fluctuation give rise to the constraint on the anisotropy of the present universe. The formula is as follows. So if you take a typical value, this is quite tiny, quite small. Okay? Thus, we can conclude that there is no primordial region of violation of the cosmological principle. That's all. Thank you.
Okay, thank you, Jiro. So is there any questions and comments? And there is one question from Thiago. So Jiro, could you see on the right bottom side of the menu so that there is a Q&A down right side?
Q and
Yeah. Yeah, there's one question from Tiago.
okay. Bianchi 1 is not conformally invariant, and thus F star F does not have this conformal symmetry. So why do we need to couple F star F with a scalar field? Okay. You're right. In case of Bianchi 1, there remains metric in the action, but I think if you don't couple the in front to the gauge field, the anisotropy of the Bianchi type of spacetime decays because there is no source of the anisotropy. We coupled, we used the gauge kinetic function to enhance the gauge field. So that gauge field supports the anisotropy of the spacetime during the inflation. So we need to couple, we need a gauge kinetic function for that purpose.
Oh, and there is one more question from David Wilshire.
How do you measure sigma over h in the present universe? I'm not sure. So maybe somebody tell me how to measure sigma over h. Probably in the context of the anisotropic inflation, one way is to measure the statistical anisotropy of CMB. From that, you can infer the spacetime anisotropy. I'm not sure if we can measure the sigma over h directly. Okay.
Okay, so any other questions to Jiro? Okay, so if not, let's thank Jiro again. Thank you very much.
Thank you very much.
Okay, so I think Prabha is here.
네,
Oh, Prabha is here. Very good. So
Yes, I'm here.
yeah, very good. So how is possible? So Prabha, now you can share your screen.
I think the previous speaker's screen is still shared.
Okay, then could you, Jiro, could you now stop? Yeah, oh yes, very
Okay.
good.
Oh. I need screen share access from the organizers.
Oh, you can't do it? Let me see.
Yeah, says disabled.
you should have it, Prava. Your co-host.
Yeah, now you're a co-host, so you can share your screen.
Oh, I'm still not able to. Okay.
Oh yeah, now you are sharing screen. So now it's working, right?
Yeah, so
Okay.
what I actually wanted was access on the laptop. So I'll just check here. Where is my... Okay, is my screen visible?
Yeah, now it's visible. So, okay, very good. So the next speaker is Pravabati Chingangbam from Indian Institute of Astrophysics, and she will be talking about statistical anisotropy. So please go ahead, Prabha.
Yeah, thanks, Jinok. Good morning, everybody. I would like to begin by thanking the organizers for their kind invitation, Stephen, Oyen, Shaheen, and all others who are involved in the meeting, organizing the meeting. So I'll be speaking today about testing statistical isotropy of cosmological fields. I will take a slightly different perspective, which is that of constructing a geometrical statistic which can capture the information of statistical isotropy, or to look for departures from isotropy in the observed data. Okay, so the like we heard in the previous talk, the cosmological observables can be viewed as random fields, and they are supposed to have been generated by some random process in the very early universe. For example, the current mostly accepted belief is that inflation or inflaton fluctuations generate these fluctuations. Then subsequently, physical interactions will evolve the primordial fields and cause modulations of the inherent physical correlations. So the correlation lengths will vary as a function of time. Then by the act of measurement or by the act of smoothing that we carry out to throw away information on small scales, we will introduce extra correlations. So below here, I am denoting by F the field. So the picture is depicting examples of cosmological fields, CMB, galaxy distributions, or hydrogen intergalactic gas, and so on, at various stages of the universe. So when we think of these observables as random fields, we have the field F as a function of spatial location, X. And what we are assuming is that we are given a probability distribution, the joint probability distribution of the random variables at different positions on X. So by the curly P, I'm denoting the probability distributions. And it contains the cross correlations of the random variables at different physical locations. So the xi, x2, and so on, except are the physical locations. So the correlation function will contain the physical correlations which are present in the field. Okay, so given this, the cosmological principle, the usual statement, of course, is that all positions and directions are equivalent, and all endpoint correlation functions depend only on the spatial separations between the points. There is no dependence on exactly where you are located, or where the observer is located, or the direction in which one is looking at. So in what I'm going to talk about today, I'm going to propose a corollary statement of the cosmological principle, and that is that for any homogeneous isotropic random field, there must exist a geometric object which is invariant under translations and rotations. So when we are given a homogeneous isotropic field, this is what we expect, that out of the fluctuations of the behavior of the random field, somewhere in the geometric, in the way the field is distributed, we should be able to construct an object. So what I have in mind is something like a circle, or if there is departure from isotropy, it will be an ellipse in 2 dimensions. And if we are talking about fields in 3 dimensions, then what I have in mind is like an ellipsoid and and a sphere. So what I am going to talk about now is, given a random field, the first part of my talk will be focusing on how do we have an explicit construction of such a geometric object. And the second part will be on applying that construction to testing statistical isotropy of the universe using observed cosmological data. So to carry out this construction, the basic thing or data that I will use will be excursion sets. So what are excursion sets? Excursion sets are basically level sets of a field or any function. We choose levels of the field or take field values and consider only points which are above that level, and we consider special regions where the field has values above that region. So that is demonstrated by the picture on the bottom left. These are showing different, for a function, the dark red is a function, and the blue planes are showing the slicing of the function at different levels, and the gray regions are the excursion sets. And so what we are interested in is the geometry of the excursion sets, geometry and topology actually. For example, you can see one connected region, and as you change the level, you have two connected regions coming up. So when we apply this to random fields, the picture on the right is showing different contours or the boundaries of the excursion sets, and the color is showing different levels. And so we can see that we have a very rich set of curves. This is in 2 dimensions, and we are interested in giving a construction of the isotropic homogeneous isotropic geometric object using these curves. So let's get into the discussion of how we do the construction. So the mathematical quantity that we will use for doing this construction is what I call as Minkowski tensors. So let me just briefly explain what is Minkowski tensors. So the picture on the left, the green, is depicting a structure which is a subset of the space. And so this structure can be either a connected region or a whole. And so using this on the boundary, we can define on the boundary curve, we can define the tangent vector and the unit normal, unit tangent and the unit normal. So on the right, in the box, I have these formula which are describing various objects, various mathematical quantities that we can define for the structure. So I will just describe that what R means. R is the from any origin. What is the position vector? This is in flat space. R is the position vector. dA is the area. dL is the infinitesimal arc length on the boundary. And the kappa, which is there in the third expression, is the curvature along the boundary. So I will be only interested, so I will not go into too much detail of the others, but the physical content is that, so below in the box below, I'm using a slightly different notation, curly 0, curly 1, and curly 2. And these are the 3 of the expressions which are at the top for different m and n integer values. So these contain the information about the area, the length, and the count, which are the Betti numbers and genus. So what I am going to use for this particular talk is W1, which is basically a matrix. Since I'm talking in 2 dimensions, this will be a 2 × 2 matrix. And the trace of that 2 × 2 matrix gives the perimeter of the curve. Okay, so this curly W1, it provides us a measure of anisotropy of the curve. So it basically it encodes the integrated shape of the structure. Okay, so let's let's take a look at how it encodes the anisotropy. So W1 in the first expression, I have written it as in terms of, I have introduced three variables, tau, G1 and G2. Basically what this is doing is I am expressing W1 in terms of a linear combination in the polymatrices. So tau is the information of the trace, and G1 and G2. So G1 is the difference between the components, square components of the unit normal vectors, n1 square and n2 square. And G2 contains information of the cross correlation between the two components. So if we diagonalize this matrix, then we can express in terms of eigenvalues lambda 1 and lambda 2, or the quantity G, which is just the square root of G1 square and G2 square. And the orientation of the ellipse, or sorry, not the ellipse, or the curve will be contained in phi, which is the half of tan inverse G2 by G1. So G, phi, and alpha. So G1, G2, basically, these are coordinate dependent measures of intrinsic anisotropy of the curve. Phi is the orientation. And I have also defined a quantity alpha, which is the ratio of the two eigenvalues, with the assumption that lambda 1, with the definition that lambda 1 is smaller than lambda 2. And if this can be expanded as 1 minus G by 2 tau. And so this, so to look at to quantify the anisotropy of the curve, we can either use G or we can use alpha, which is the ratio of this. So G and alpha are coordinate independent measures of intrinsic anisotropy of the curve. So before we move ahead to applying this to random fields, just for the example of the single structure, so we can show that if the curve has M-fold symmetry with M greater than or equal to 3, we can show that this W1 matrix is proportional to the identity matrix. This is quite easy to show. That's the first thing. So any curve, any closed curve that has M-fold symmetry will have one identity, will have W1 identity. The second point is that W1 provides a mapping from any arbitrary curve to an ellipse, and that ellipse is unique up to translations of the centroid. So these are two results which we will use. And here in this plot, I'm showing just to compare for ellipses. As we increase the aspect ratio of the ellipse, that means towards, on the x-axis towards 1, the ellipse is becoming more circular. So 1 is circle. How alpha behaves and how it compares with the ellipticity E. So it is equivalent to the ellipticity. Okay, so now is my screen visible? Okay, so now what we need to apply to random fields is W1 for many curves, because a field at any excursion set will consist of many curves. And so we can consider W1 to be, now I have changed the notation of the integral over C to partial Q, which means the boundary of the excursion set Q. And so this can be interpreted as the sum over the different, tensor sum of the different curves. So for a random field, what we are going to have are what I am denoting by nu is the normalized field threshold value. Normalized means that I'm considering the field to be divided by the its sigma standard deviation. And I have boundaries of excursion sets as a chosen nu. And so when we do this computation of W1 will become a function of nu. And this is what we are after. So in the figure above on the right, what I'm showing is a collection of many curves, such as what we expect for random field, which can be arbitrarily shaped. And the arrows are indicating that what I talked about earlier, that we can map each curve to an ellipse, and they can all be superposed and to obtain a final object, which is the big ellipse there. Okay, so before applications, we would be in, so I mentioned that we are interested in constructing a geometric object which is isotropic. So one thing that I did not mention earlier is that W1 is by definition translation invariant, or on, so since I'm interested in applying this on the sphere, it will be, what it means is that it is invariant under rotations which move the centroid of the curve. Okay, so what we can show for isotropic and Gaussian random fields, we can actually compute the ensemble expectation of W1, and it is given by this formula here. So the threshold dependence is encoded in the Gaussian function, and and the cosmology dependence is encoded in RC, the factor 1 by RC. And what is RC? RC basically is the correlation length of the field. So it encodes all the cosmological parameters, and the physical interaction length that has gone in will be encoded in this. So RC is the ratio of the standard deviation of the field and the standard deviation of the first derivative of the field. So they are given here, sigma 0 and sigma 1. Sigma 1 is given as the sum of the standard deviation of first derivative and second derivative. So if the field, if we assume for a given field which is isotropic and Gaussian, the Gaussian functional dependence is given by the exponential Gaussian part, and the isotropy is given by the fact that W1 is proportional to the identity with identity matrix. So as a consequence, if I were to construct alpha, the quantity which is the ratio of the eigenvalues, it will be 1 at every threshold. So this is what we expect for a random field, which is really exactly a Gaussian and isotropic. Okay, so for practical applications, of course, that is not going to be very useful. In practical applications, we always have data on a finite extent and also pixelized. So it means that there are two length scales there, the size of the box or region of the sky that we are looking at, and the pixel size. So this is what I mean by finite sampling. So what this does is, of course, that it will break the isotropy. And so what we have computed is the ensemble expectations of the different isotropy variables that I introduced, which are elements of the W1. So let me explain first the equations on the left. So G1 as a function of threshold, I have shown here the modulus, and this means the bracket means the ensemble expectation value. So we can show that. So these formula are basically G1, G2, G. These are from numerical computation. We have not exactly analytically computed this, but we have found that they are fit very well by G1 and G2 are fit very well by Gaussian functions. And so we have two parameters here, the amplitude of A and of G1 and G2. And there's a sigma which enters in the expressions. So the right-hand side shows there are two columns for the two different smoothing scales, 30 arc-minute and 90 arc-minute, and it shows how well it is fit by these functions. So once G1 and G2 is known, G is given in terms of the parameters of G1 and G2. And so tau is basically the perimeter, and the expression for tau for exact isotropy for Gaussian field is of course well known. It is one of the Minkowski functionals, the scalar Minkowski functionals. And so what we find here is that from this finite sampling will introduce a slight departure from the formula that we are all familiar with. And so this provides us now next a formula for the ensemble expectation value for alpha. So alpha has this form, which is as a function of nu. It is 1 minus an amplitude which determined by the amplitude of tau and g, and an exponential function. Okay. Then it is also interesting to look at how the amplitudes of g and tau scale as a function of the resolution. And the left-hand side is what it shows. So we find that the amplitudes of tau and g exhibit Paolo scaling with the smoothing, and the sigma g, on the right hand side, it shows how the sigma g scales linearly with the smoothing scale. And tau is of course, sigma of tau is of course close to 1 as is expected. Okay, so here is the essence of the construction that I talked about, how we represent a random field by the geometric construction for each isotropic random field. So this is the random field. So even if the field is given, or the power spectrum and so on are given to be isotropic, when we have a field when we are sampling the field on finite, using finite resolution and on a finite extent, what we can construct is only ellipses, and the ellipse. So here you can look at each row, and each row is corresponds to one random field at a given resolution. So S is the y-axis. S represents the ratio of the two scales, the pixel size or smoothing scale, and the size of the box that we are interested in, finite extent. So for each such resolution, the field can be represented as a series of ellipses, and it is the ellipticity is least elliptic or closest to circular behavior at threshold mu equal to 0. And then as we increase the threshold or decrease the threshold, it exponentially drops it becomes more and more elliptic. Okay, so this completes, okay, I have one more slide it is also important to look at how the statistical behavior of each of these parameters when we apply it to observed data. So the probability distributions of the G1, G2, so these are constructed from many simulations, 10,000 simulations. So what you can see here is that G1, G2 roughly follow Gaussian distribution, distributed about 0. And because of that, G is Rayleigh distribution. So which means that the orientation phi will have uniform distribution. Then in the line, in the second row, we have the PDF for the tau, for the trace, and the eigenvalues and alpha. So since my talk today is about the interpretation of alpha and applying to data, it's important to note that alpha does not have the Gaussian distribution. Of course, it is between 0 and 1, it distributed between 0 and 1, and it roughly follows the beta distribution. So this different tails is important when we interpret, use alpha to make statements about observed data when we are searching for departures from isotropy. So that concludes the first part of the formalism, where we are developing the method. So I'll now move to applications and how we use this construction to look for departures from isotropy. So the first application we have made is to the Planck temperature and E-mode data, 2008 data this is. So the plot on the left is showing the result for temperature. And the different colors are the different blue, red, and green. These are showing the different component separation pipeline Planck data. So we have shown it for one of the frequencies. So, and the black dots are the Planck simulations that the Planck team has provided, which one can use to compare with the observed data. And the error bars are the 1 sigma. On the right is the E-mode data. And this is only for SMICA simulation. The red is the SMICA simulation, whereas the other showing the error regions are the different different simulations of the data for comparison. So the conclusion that we get from here is that in this year, when we look at the chi-square distribution, how the deviations are and so on, we find that there is no statistically significant deviation from statistical isotropy. SI refers to isotropy. So this is work done by my student Joby, whose picture is here, and I believe he would be in the audience. The next data that we said that we have applied to is the Planck convergence maps. So this slide gives a description of the lensing of CMB maps, CMB photons by, the picture is showing CMB photons by last scale structure on the way. So the box is showing, in the image, the box is showing the last scale structure distribution and how it gets, how the photon parts are deflected. So the data that I'm interested in is what is called the convergence. So here in this slide, let me just go down to the equation below. Phi is the lensing potential, which is the integrated potential over the line of sight, and kappa is the del square of phi. And so this is the convergence, and this is what we are interested in. So this data is given by provided by the Planck team. Okay. So so the Planck team provides the FFP10 simulations also, with which one can carry out a comparison. So this is work done by Priya, my student Priya. So what I have here is the global analysis, which means that I am using the map over the whole sky. And so we looked at the different, so that you can see that there are two rows of plots here. The first plot is the without any Wiener filtering, so which cuts down on the noise, because we know that the noise, Planck convergence noise is supposed to be, Planck convergence map is noisy. And the below one is the Wiener filtering. So here what you can look at is the chi-square values. So I have used a slightly different notation from before, the chi-square tilde with the subscript 2. So this is basically we are looking at the value 1 and -1 are departures from 2 sigma, 95% confidence. And since, like I mentioned earlier, we are looking at whether the deviation is on the positive side or on the negative side, because the alpha is the statistic alpha does not follow Gaussian distribution. So just to keep that in mind. So we have, what the conclusion from here is that there are hints at specific thresholds, but the information of because of the global analysis, we are integrating over the entire sky, we can lose information. So we follow it up with a patch analysis. That means we split the sky into smaller patches and we look for, we carry out a comparison of alpha. So here the picture is showing the results of our analysis. The yellow parts are so these are the first row and the second row are clearly, you can see that the patch size is smaller. So these are two different resolutions. And in the upper part, you have two maps, and those two are referring to, on the right, we have more finer sampling of each patch. So number of pixels is higher on the right. So we carried this out and we are able to identify several patches which are showing deviation from statistical isotropy, expected statistical isotropy. So the yellow, the color coding is that yellow is basically between 2 and 3 sigma, higher than 2 sigma, but less than 3 sigma. The red is higher than 3 sigma, and the blue is also higher than 3 sigma, but on the negative side. That means the alpha value here is lower than the one from the simulations. So we have these different patches. And so, so we have found these patches. So in the conclusion, what we find is that most patches, of course, you can see they have value higher because they are yellow or red, they're higher than expected. So this, when can such higher than expected happen? So this can happen when when the data contains, when the observed data contains, say, relatively more number of structures compared to than the simulations expected from the simulations. And this can happen, this can be explained. This is not the final thing, but it strongly indicates that this is inaccurate instrument noise estimation. Then we have two patches, the blue ones on the left bottom, which are showing where the alpha is lower than expected. And so this we would take a little bit more seriously as indicating true departure from isotropy. However, with the analysis that we have done, we cannot conclusively say that this is because of true departure from an isotropy, or it can be also noise. So this needs to be probed further. The last application is for the purpose of foreground component separation. So usually when in the CMB foreground component separation, a usual template that is used for the synchrotron map is the Haslam data, which is all sky data at 408 megahertz. So and the assumption is that usually this is extrapolated to the CMB frequencies, and the usual assumption is that on small scales the data should be, the synchrotron map should be isotropic. So we want to carry out a test of that using this methodology that we have developed, and this slide is showing that comparison. So on the left, there are many colors, so I'll just explain quickly. The red, so basically we throw away large scale structures and very high emitting regions, high intensity regions. So the red and the green are two different cases where we are throwing away above 60 Kelvin and above 25 Kelvin. So you can see that the red, of course, as we keep high intensity and large scale information, the data is highly anisotropic. But then when we go down to small scales, on the right, I have the chi tilde, which is basically the deviation from 2 sigma for different LC. So LC is a cutoff for the large scale information. So we are showing 3 different scale information. So as you go on the right, we are going down to smaller and smaller scales. So what we can see is that the data becomes more and more isotropic on small scales. And so the assumption of isotropy is okay, so it is fine to take it. However, we need to it would be interesting to carry out the patch analysis, because this is again a global analysis, and we may be losing information by doing this. Okay, so that brings me to the end of my talk, and here is the summary. I hope I have not exceed, oh, I did exceed time. Okay, so what I've talked about is that even though I didn't speak about the entire Minkowski tensor set, the entire set is actually very useful. It enlarges the statistical tool set for analyzing cosmological fields on pixel space, and provides information about the structures in isotropy and as well as Gaussianity. So it's a neat package, and these are quite intuitively simple and elegant, and we can carry out analytic predictions to a large extent. Then the content of what I have spoken today is that we have used this, what I call as the contour Minkowski tensor, the W1, to construct ellipses, then encapsulate the statistical isotropy of random fields. And we have taken into account the effect of finite sampling. And from the Planck convergence data, we have identified sky patches which exhibit anomalous behavior and needs further probe. Thank you.
Okay, thank you very much. There's one question from Takahiko. So Prabha, could you take a look at the Q&A on the right bottom of the menu?
Yeah, I'll just do that. Okay. Do Minkowski tensors have more information than scalars in an isotropic? And generally, no. Yes, definitely they have more information, but so there are two aspects. One is if we are looking only at non-Gaussianity or the Gaussian information. So what the Minkowski tensor Minkowski functional is doing is to split the components which we are familiar with in the scalar Minkowski functionals into two components in terms of for 2D and 3 for the 3D. So the scalar Minkowski functional are basically traces of the tensor Minkowski. The particular tensor Minkowski functional I showed, the trace of that gives the scalar Minkowski functionals. And so when we are taking the trace and adding over the components, we are losing information. But the complication is that since this can be, when we do Minkowski tensors, we have to be careful about the coordinate dependence of the components. So when we interpret data, we don't want that to confuse. But yes, there is more information, and one can do a Fisher matrix comparison of the different information content. So one does expect that, for example, error bars will shrink if we are in 2D. If we are looking at Gaussian information, we expect that it will go down by 1 by square root of 2, or in 3D, 1 by square root of 3. So that's about the Gaussianity part. Now, what is really not there in the scalar Minkowski functional is the information about the anisotropy. So because the scalars are scalars, they don't have the direction information, which is there in Minkowski tensors. So that is completely new. And Minkowski tensors, we can look, the anisotropy information can be looked at in two ways. So I have spoken only about the relative alignment of structures. So I did not discuss the individual structure shape, how it gets distorted, and that has additional information about how physical effects can induce distortions and shearing of structures on an individual level. So that is there. One thing that for comparison with scalar Minkowski functional, what we can do is also one can compare with the ratios of for example, if you are looking at filamentarity shape finders, I think that's the word people use in the literature. One can construct shape information by looking at ratios of Minkowski functionals, the scalars. So one can do a comparison of that with Minkowski tensors, the information or alpha and so on. So the shape information is there in scalars, but does not give the orientation information. So Minkowski tensors that provide that as a unique, genuinely new information. So I hope I have answered that question. Shall I read out the next question?
Oh, yes, please.
Okay, so on slide 10, the error bars are increasing with smoothing scale. Slide 10, okay. Is this, oh, okay, the sigma, I guess the sigma, yeah. So basically this can be explained by the fact that when we go to larger smoothing, the number of structures is decreasing. So the statistical information is less. That is why it increases with smoothing scale. Okay, any other question?
Okay, so is there any other questions or comments? Okay, if there is no more, then let's thank Prabha again. Thank you very much.
Thank you. How do I unshare this?
So probably the main organizer, Stephen or Erwin, will be directing something about the discussion, the following discussion session. Or do you have anything to say about that? Some practicality.
Actually, Jinok, I think you could basically share it. Do you want to start now, or?
Oh, well, let's go ahead right now.
Actually, I had a question for Prava. Prava, it was just to basically get it rolling. So basically, you point to certain points on the sky where basically it's anomalous. Can you correlate that with other, observations of it being, other, say, in other data sets, or
yes,
or is it just some isolated thing that we should just dismiss, right?
No, it should be correlated, and we haven't done that yet. So we hope to do it soon. That's the next step. It should correlate with other structures.
Prava, Stephen.
Yes.
So
yeah.
Are the directions, are they similar to any other known anisotropies in the CMB, like the power asymmetry or anything like that? Do you see the power asymmetry?
Actually, no. So I pinpointed basically the two which I believe is truly anomalous, in the sense of the alpha is lower than expected from simulations, and those are one is in the not ecliptic plane, not ecliptic pole, and the other one lies along the ecliptic plane. So there may be some reason which is connected with the observation, strategy and so on, which it is not clear to me as yet. So I hope to understand it better. Actually, most of the patches that I showed, they have something to do with the ecliptic, but they are not in the same direction as the other anomalies, like the same dipole.
Okay, so you don't see that. Is that, shouldn't you see it? I don't know why you wouldn't see it, because there's more, it's telling you basically there's more structure.
Yes, yes. So I think we'll be hearing more about the dipole in the afternoon, right? I was indeed expecting that there should be, there should be some correlation with that. But I think the reason is that the convergence map that is provided by the Planck team, it is extremely noisy. So the signal to noise is 1 at around L60. And so we have mitigated it by using Wiener filtering, but I believe it is not enough. So basically, what we are probing has to do more with noise than true anomalous behavior in matter distribution.
Okay.
Yeah, over to you, Jinok.
Yeah, so as you see, this discussion session is to promote the our questions regarding the fundamentals of the assumptions on cosmology, that is the homogeneity and isotropy and etc. about the cosmological principle. So if you have any questions, well, you see that all the speakers of the meeting, including today's David, Jiro, and Pravabati, are all specialists in their own regarding various fields. So if you have any questions, or you want to argue, or you want to say defend the cosmological principles, it's also all up to you. So I guess my role is to promote arguments and bring conflict, right? So it is very highly encouraged. So please ask any questions or attack the speakers. And yes, please. That's what we are expecting in this meeting. So,
can I ask a question quickly? So I may as well start. So I've got a question for David and also Dragon, related to a comment that Dragon had. So they say that most large-scale structure catalogs see this excess power on large scales, and it could very well just be some systematic in data. But the fact you see it everywhere, and I know that they saw a large-scale power excess in the BOSS data, and they tried very hard. Various groups tried very hard to treat the data and clean it, but they still find a large-scale excess. So I wonder, Dragon said it's fine, don't worry about it, but I wonder to what extent, at what point do we have to start thinking that there is large-scale power excess, and what needs to happen for that to become a signal rather than just dismissing it as systematics?
Yeah, good question. I mean, I can say a couple of things. I guess I wouldn't say completely don't worry about it, but rather it's unsurprising that it shows up. It's just kind of a guaranteed product of various systematic errors, all of which happen to look like large-scale systematics. The first paper that was pointing this out goes back into the late 90s. It goes back, and then you have a whole history of early Sloan papers and later that seen or would have seen this signal had they not done various increasingly more sophisticated methods of cleaning the maps. And that's what we've done with the dark energy survey, and I think that's what everyone has to do at some level. Now, your question is excellent. When you've done some cleaning or enough cleaning and mitigating these errors, and there's something left, should you be worried? And yeah, there would be an exciting possibility that there's there. I think it's going to be extra hard to convince yourself at large scales that you're seeing something primordial, just because there are these guaranteed sources of systematics. But that's an excellent question you're asking.
Okay, can it be related to non-Gaussianity at all, like primordial non-Gaussianity?
Right. Also, this is what makes primordial non-Gaussianity measurements tough, because they are kind of exactly that kind of signal, that you expect a bump on large scales. And now that's exactly the part you have to clean up systematics. So
okay,
that makes, yeah, it's all mixed in together.
Yeah. Okay. So, but in your experience, the dark energy survey, there's no this large scale power asymmetry excess is under control.
Yeah, we've had a major, a little more complicated to explain, systematic in our key paper, year 3 key paper that came out in May. A major surprise. It was effectively a nuisance parameter that you expect to be unity in the standard model that was discovered at 5 sigma. So it's basically, we saw 5 sigma effect of some sort, but it's almost certainly not primordial, and it's not at large scales. It's a more subtle thing having to do with various combinations of lensing and galaxy clustering.
Okay, thanks.
Just to follow on a little bit, I think there are other opportunities to get past the systematics, because we wouldn't expect that the systematics occur for an individual data set, right? So the systematics for BOSS, for example, to do with stars, don't worry us in the radio, right? We don't see stars in the radio. So there are opportunities for detection of cross-correlation, which should be relatively systematic free. The trouble is that when you measure cross-correlation, there are other physical effects that creep in, things like magnification or ISW or something. And so while you might be able to get around some kind of excess power, some kind of systematic excess through a cross-correlation of very different traces, you also then have different physical effects creeping in as well. So there are these multi-tracer, like, so if you had a sample which were taken in different manner, which also sort of were tracing the same density field, right, where you didn't have to worry about magnification, which were covering the same sort of three-dimensional region, then you might have something which was, you might trust a little bit more, but that would be really hard to generate. Maybe with like H1, right? But even with H1, you don't. So if you had like an H1 sample and an optical galaxy sample, but it would be really hard to do over a large scale and a large volume.
Yeah. Okay, thanks.
And there is one question from Junsup. It's to Prabha, and I think the question is also a bit relevant for David. So Prabha, could you first answer Junsup's question, and also David, could you leave some comments later? So Prabha?
Yeah. Yes. So the question is, can we apply the statistics to galaxy surveys? I guess gravitational evolution introduces anisotropy, which is not primordial. So yes, of course, it can be applied to any large survey, and we are actually doing this. So Stephen is leading the discussion or the investigation of this kind of question. So he's already doing that. Radio surveys, yes, we have also applied. We have not applied to actually observe data, but we have applied this to 21 centimeter brightness temperature fields. And there the application we have done so far is to constrain the parameters of the models of the EOR. Okay, I hope that answers the question.
And David, do you have any comments on Junsup's question?
Yeah, I mean, I think this is a great opportunity, especially for something like 21 centimeter at very high redshift. There's another opportunity to measure this beyond just the CMB. Would be great.
Can I just comment quickly as well that so I've been applying this to galaxy data, nearby galaxy data, so SDSS main galaxy sample and BOSS, and the data is intrinsically anisotropic and inhomogeneous because it's in redshift space. So the dominant redshift space signal in the nearby universe is just these like the spherically symmetric redshift space distortion signal. So whether you can check primordial anisotropy, we have to remove the anisotropic component we know about, and it's very difficult because the true signal, redshift space distortion signal, is inhomogeneous because it's radially symmetric. So we're currently working on that. But yeah, I hope so. I hope we can treat that as a systematic and remove it, and then look at what's left.
Okay, great. And another question from Jenny. I think which is a very relevant question, probably to everybody here. That's about the comparison between the standard spherical harmonics decomposition and Minkowski functional eye approach. So probably Prabha and Stephen should be able to say something about this question.
Yeah, I can answer one part. So for example, I can mention that when we look for an isotropy deviation from statistical isotropy in the CMB, the use of spherical harmonics, it is used by looking at instead of CL, you can have CLL prime, MM prime. So the correlations between the, we don't sum over the M's, and typically that is called the bipolar spherical harmonics. And one looks for non-zero terms for the different M and M primes. Yes, they should be consistent if there is any anisotropy, but the systematics are quite different because the Minkowski functionals integrate over all the L's. So from the expression that I showed, Minkowski functionals typically depend on sigma 0 and sigma 1, which are integrals over the L modes. And so the way in which the information is extracted out from the data is quite different. So when we look at the spherical harmonics, we are looking at it mode by mode, whereas in the Minkowski functional, we are looking at integrated effect. So I would believe that the Minkowski functionals tend to lose some information when integrating out, but when looking for information which is not specific, just to do a blind search, I think the Minkowski functional would be more useful at finding those that kind of information. So that's about the systematics. So the systematics are quite different. One way in which we can sort of bridge the gap between these two is by using what I call need-led analysis, which means that the data in real space, one can do a decomposition and pick out, using need-led transformations, to pick out scales which are specific to localize in L. It is localized in space, real space, as well as in L, and one can do a comparison. So such an analysis can make the two ways of analyzing closer, and it makes it easier to compare the result. Yeah, so that's all I have to say on this question, I hope.
So Stevens, can you add a little bit here?
Yeah, I think Prav's answered the question. I don't know, in terms of, we're talking specifically regarding anisotropy, or if you're disregarding the field. So there's different information in the Minkowski functionals compared to just the power spectrum. So you can actually test for Gaussianity in the CMB map, for example, and people are doing that. And you can do that with Minkowski functionals because you don't assume that it's Gaussian, but the Gaussianity produces a very specific signal, and non-Gaussianities will be detected, using shape information in Minkowski functionals. So I'd say that in that sense, it's they are complementary to the 2-point statistics, and also they're sensitive to different cosmological parameters. So you get maybe different information. If there's some tension or whatever in data, then you can maybe look at you get a different sensitivity to different parameters. So you can you find out more information in that way. But in terms of, well, the other thing I'll say is that the Minkowski tensors are intrinsically, they're almost by design intended to detect anisotropy in the signal in data. So I think they are a natural statistic to use if you're looking for anisotropy. That's all I've got to say about it. Thanks.
Okay, so any other questions you want to ask the speakers of the day?
Gino, I have a question. Actually, it's to David. David, that was a very nice talk. We have this A lens anomaly in Planck. If we look at this excess at I guess at large scales, can you imagine it being connected to this A lens anomaly? Or maybe to Dragan, if you want to jump in there.
My answer is no. It's not. It's not.
It's a very naive question, right?
No, it's a different kind of behavior. The A lens is because the CMB. So the A lens really comes out of the CMB higher order statistics. So they measure the trispectrum, the 4-point correlation, in order to reconstruct kappa maps. And the correlation of the kappa maps has an amplitude. And they measure that. So they get this value of A lens, which is very high. But that's only from Planck. I think actually other CMB experiments have done, on the smaller scales, have done a similar thing to reconstruct the convergence maps. And they found a A lens which is different to the one that Planck measures. I don't think there's convergence on the A lens at all. Dragan probably has a better perspective on this than I do. Do you have any comments?
No, I don't have any insight on that.
Sorry, David, can I also ask about declination? You had a look at declination with your excess. Can you explain why that was done?
So if you point your telescope at something which is directly ahead of you, above you, or you point at something which is much closer to the horizon, you have a very slightly different beam footprint. And we wondered if we were getting slightly different, because our prediction is based on noise. So if we have slightly different noise as a sort of angle that we're observing on the sky, azimuthal angle, then you might expect to see slightly different numbers. So it was just a sort of basic observation cross-check that we wanted to do to see if there was some observing angle dependence on that large scale power. The trouble is, though, that our noise model should in principle take into account the fact that we're observing at a different azimuthal angle. And certainly we do see the excess in the randoms as well. There is, if you look at the number distribution as a function of declination, then it does change because the noise changes. Because if you have a distorted beam on the sky at different declinations, then you're going to get a different noise signature. So even though this is involved, this is taken into account in our noise model, we still see an excess power. So it was a cross check that I thought would yield some insight into where the systematic is coming from, but no strong conclusion. Unfortunately, we couldn't get any strong conclusion from it. It seems to be above what we'd expect given the noise model that we have on the sky.
Okay, can you also look at right ascension, or it's impossible, right? You could only look at declination.
No, sure, we could. I mean, this is just a subdivision of our catalog. I think we did, I have to remember now, I think we did do strips and right ascension at all as well. And we found, again, just kind of noisy. There was no trend with right ascension as far as I'm aware.
Okay.
I'd have to double check with my team, but there was a slightly more convincing trend with declination, and there wasn't really a noticeable trend with right ascension.
Okay, so any other questions or comments?
I have a question for Prava, but
let me just remind participants that you can just jump in, right? While we're at it.
Stephen, you had a question for me?
yeah, I was just waiting to see if any of the attendees had a question. But so alpha, right, and the eigenvalues of your Minkowski tensor, is like a measurement of intrinsic anisotropy. Because so if you have a finite volume or a finite area, your field won't be perfectly statistically isotropic, right? That's the point. In the same way that it's not ergodic if it's a finite volume and you measure it. To see if there's an anisotropy in the data that's beyond what you expect, you need to know what alpha should be for, you know, the idealized case. You need a prediction for what alpha could be.
Yes.
So we don't have one of those yet, unfortunately. So have you made any progress on like calculating the ensemble average of alpha, basically, all the eigenvalues? Could you talk about that?
Yeah, that's a very, very hard thing to do.
Yeah.
And so what I showed in the talk today were like what I refer to as semi-numerical. So we use the numerical calculations to guide us to the analytic expression for alpha. But that is not the same as deriving them exactly. And I think the progress is not very much in that direction. We've been trying. But the analytic expression, basically the one I showed is alpha goes as 1 minus there's an amplitude and it's an exponential function without the minus sign. So e to the power, I forget now the expression. Okay, so there are two parameters there. The understanding of alpha comes from understanding of the quantity g, which is the amplitude of the true tensorial part of W1. There's a square root of G1 and G2. So it depends on the amplitude of that, how that breaks the isotropic expectation. And the second term that is important is in the how the anisotropy will split, will make the amplitude of the contour Minkowski functional, the scalar one, deviate from the expected form. And well, in the paper we have an expression for it for anisotropic, but the progress is we have made some progress, but it's not the full progress. Yeah, a lot more work and understanding still needs to be done.
Yeah, it's related. It seems to be related to the statistical uncertainty on the Minkowski functionals, right? Because it's the
yes, it is. Yes.
And I was actually hoping to ambush Professor Takehiko Matsubara. So I know he's in the audience, and I heard that the group he was working with some members of in Paris trying to estimate the statistical error on the Minkowski functionals for a Gaussian field. But I don't know if there's any progress on that.
I can see his name in the audience.
Yeah, I shouldn't ambush attendees. I was just curious. Anyway, I think we need the 2-point function. We need the information on the correlation function of the excursion set boundary. That's my understanding.
Yeah.
Which we don't have.
Well, the idea that I'm trying out with is to have an understanding of splitting the sky into independent sky or your sample space into independent components, and use that to infer the statistics of, for example, if you are if you're asking what is the probability density function for sigma 0 or sigma 1, for example, the idea that I'm experimenting with is it feasible to work that out as a F, and the ratio of that as the something like the F distribution, and use the number of degrees of freedom as the from the independent components by using the correlation length. So I'm not 100% sure it will work, but that's what I'm trying out.
Okay, thanks, Prabha.
Yeah.
Okay, so any other questions or comments? Okay, then I have one question for Jiro. So you talked about the gauge coupling between the inflaton and the gauge fields. So is there any possibility that by setting up the model in your model in such a way that the signal is stronger in some different observational wavelengths in the later stage, for example, in a radio radio wavelength or something like that? Jiro?
Sorry, the internet connection was not bad. It was bad, so I couldn't hear your questions.
Okay, so my simple question is, in your model, by tuning a little bit for your gauge field, is it possible that some signal is stronger than in the CMB than some different wavelengths, for example, in the radio signals or something like that?
I think it's possible because so the timing, where the gauge field becomes important can be tuned by choosing the appropriate gauge kinetic function. So yes, you can design so that at some frequency range, the signal is strong.
So what is the main parameter you can tune? Is it the coupling or what?
Yes, I think a functional form. You can choose functional form of the gauge kinetic function. So that the first part of the inflation gauge field is not important, but later gauge field becomes important. Then in that case, on short frequency range, you will have this strong signature.
But then the question is, what is the principle we can choose the gauge kinetic function, isn't it? You can, very naively thinking, there could be some millions of different choices.
Yes. So since we don't have the fundamental theory to predict the gauge kinetic function, so at this stage we have to choose some gauge kinetic function. Then of course there are many varieties to choose this gauge kinetic function. Some of them predict the strong signature on some specific scales.
Oh, okay.